Welcome to IM3, video 2 of 2. This goes with 11.2 as well. So this is the second one of 11.2. Think of it that way on your progress chart. The topic for this particular lesson is all about rotations, and there's 6 boxes for us to talk about. So let's kind of get right into it. First, we're going to talk about the parts of a rotation. And over here in this little box here that I've got in blue for you, the parts of a rotation are as follows. There's 3 main parts here, okay? First, you have to have some kind of a shape that you're working with. So for example, we have this shape right here. It looks like a flag of sorts. Here's Q and then here's R. And then there is a point about which we are rotating this particular figure. So we're going to call that the center of the rotation. So in this case, that would be P. And then we have the angle of rotation. So how much we're actually moving the entire shape. And so in this case, we're moving it an angle of 40 degrees. So we have the original shape right here. We have the center of rotation, and we have the angle of rotation. So these are all the parts of a rotation. But let's actually kind of see now what it would look like through the lens of actually doing this. So over here, I've got a figure. I've got like F, A, and E prime, and then I have this little slider here. So I want you to watch what happens as we move the slider around. You can see that the angle of rotation is changing as I move the slider. So for example, if I move the slider to 118 degrees, you can see that every single point in my original figure has been moved an angle of 118 degrees through or about the point 0, 0. And we can change any of these shapes around if we wanted to, and the rotation would still be the same. So if I made this like something that looks like this a little bit, right, the rotation would still look the same as we do it. And of course, if we rotate 360 degrees, we get right back to where we were. 180 degrees ends up in that shape, sort of in the opposite quadrant. 90 degrees, you can see looks like that. So we have all these angles of rotation are still the same here, but the parts are what's important, okay? So coming back over to our little lesson. How do we do number 2? How do we actually draw this without using sort of software like we had right there? So in order to draw a rotation of 120 degrees, the first thing we have to do is we have to give ourselves a segment from each of our vertices to our point of rotation. So our point of rotation is P in this case. So I'm going to draw a segment from C to P. So I'm going to draw a segment like that from C to P. Then I have to take my protractor, which I have over here for you. And what we have to do is we have to line up our protractor exactly on point P. And we have to rotate our protractor so that it lines up exactly with our segment. So kind of like that. And let me move it maybe down like this a little bit. So line it up and on the segment. And then what I would do is I would mark off 120 degrees. So it looks like 120 degrees would be here on my thing here. So it looks like 120 degrees would be right about there. Okay. And then I would measure the distance from P to C. And I would draw that exact same distance over here from P to C. So that right there is an angle, a rotation of 120 degrees. And then I would do the exact same thing for A and for B. So this would be point C. I would do the exact same thing for A now. So I would do draw a segment from A to P, like that. I would take my protractor again, kind of line it up in the right spot. In this case, I'd have to maybe rotate this a little bit, so I didn't do a very good job, but you can see what I would do. Anyways, the ending result would look like this image. Again, it would look just like this image. It was rotated 120 degrees. So that's probably easier to show you like that on there. But you would draw one, it's kind of hard on an iPad. But you would draw each of these segments, and you would take your protractor, and you would give the exact same measurement in that angle of rotation. So kind of a hard way to do it on an iPad, but that's how you would do it with your pen and paper, asked to on a skill check or something. Okay, so that's how you do it for box number 2. Sorry that wasn't as great as I wanted it to be. Okay, box number 3. The core concept here is there's a couple of nice little rules we can use to help us rotate for very specific degrees around the origin. So the ones that we're going to talk about in box number 3, let me zoom in for you here, are what are the rules for rotating something 90 degrees about the origin? And remember, the origin is the sort of center of where the X and Y meet. What are the rules for rotating 180 and 270? So let me walk you through each of these rules, then I'll give you an example. So let's say I have a point over here, AB, and I want to rotate that point AB 90 degrees. Well, the nice little rule says that we can take point A, B, and turn it into negative B, comma, A. So what do I mean by that? Well, here's point AB. So whatever B happens to be, make it negative and keep A the same and switch their places. That was going to give you a rotation of 90 degrees. That's a pretty cool little rule. In fact, this box is super helpful. So rotating 180 degrees, take any point AB and turn it into negative A, negative B, which makes kind of sense because if this is AB, then negative A, negative B ends up in the opposite quadrant. So that would give you a rotation of 180 degrees. 270 degrees says take any point AB and turn it into B negative 8. So if this is point AB, I would turn it into B negative A, and that would give me a rotation of 270 degrees all the way around. So this little box, very, very helpful. Make sure you have that in your notes. Okay, so box 4 here is rotating a figure in the coordinate plane. So let's use some of those rules again. So it says graph quadrilateral RSTU with the given vertices that we already have here for you, and then graph the image at a 270 degree rotation about the origin. Okay, so I already have the pre-image for you, and it's my quadrilateral RSTU over there. The other thing that we need to put on here is the origin. So remember, the origin goes at the center. And remember the rule for 270 says take every AB and turn it into B negative A. So let's do that together. So if my original point R is 3, 1, remember the A is acting like the 3 and the B is acting like the 1. Let's turn that into B comma negative A. So that would be 1 comma negative 3. So if I graphed 1 comma negative 3, that's where R prime goes. So 1 comma negative 3 would be 1 and 1, 2, 3. So that'd be here. Okay. So this would be R prime. Excuse me. S is 5 comma 1. So remember, the A is acting like the 5, the B is acting like the 1. So we're going to change that into 1 comma negative 5. Okay, so 1 comma negative 5 looks like this. So 1, 1, 2, 3, 4, 5. That'd be this one right here. And that would be S prime. 5 comma negative 3 means keep the B the same and make it first. So negative 3 comma negative 5. So 1, 2, 3, 1, 2, 3, 4, and 5. That would be T prime. And then lastly, 2, negative 1, so keep the B the same, so negative 1, and then make this opposite negative 2. Okay, easy. So negative 1, and then negative 2, 1, 2. So that right there would be our U prime. So if I connect this right here, I would have this shape, and that would be a rotation of how you would do it of 100 or of 270 degrees. So again, what we did was this, just to make sure you guys are following me along, right? So if I take that distance, go to R, and then go 270 degrees and end up here, this is what I've done. I've rotated this guy 270 degrees. So that's the rotation of 270. So this is the image, or this is the figure, sorry, that we're ending up with over here. And the original one is our blue one, and the new one is our pink one. Remember, the original one is our pre-image. So the blue one is our pre-image, and the pink one is our image. Okay, that's everything you need for box 4. Okay, box number 5 is a composition again. So just like we had compositions with translations, we can also have compositions with reflections. And in fact, this is also considered a rigid transformation, a glide reflection. So what we're going to do is, or a composite reflection, sorry. We're going to graph line segment RS, and I already have the graph and the line points set up for you guys over here. And it says graph that and its image after the composition of a reflection in the y-axis and then a rotation 90 degrees about the origin. So we're going to do this one step at a time. So first things first, we're going to reflect what we have in the y-axis. So remember, a reflection means if I am 1 unit away from my line of reflection, which happens to be the y-axis, then I go 1 unit in the opposite direction. So I would end up here. So this would be our r prime. And let's write that coordinate down. That'd be -1, -3, -1, comma, -3. So I'm going to write that down in 2 locations, and you'll see why in a minute. And then, again, if my y-axis is my reflection line, I am 2 units away from that reflection line, so I'm going to go 2 units away in the opposite direction. So this point over here is going to be S prime, and I'm going to write those locations down. That would be -2, 1, 2, 3, 4, 5, 6. So -2, comma, -6. I'll write that down here. -2, comma, -6. So that's my first reflection over or in the y-axis. And then lastly, I want to rotate this 90 degrees about the origin, okay? So remember the rule down here, I wrote it down for you just in case you forgot, and you can go back to your notes and refer. The rule for 90 degrees says take every b, or take every AB and make it a -b, comma, a. So what we're doing in green here, A is -1, B is a -3. So change the sign on B, so that's going to be a 3, and keep the A the same, but make it the second point, so that's going to be a -1. So 3, -1. So 1, 2, 3, -1, boom. That ends up being our double prime. And what this is if I draw and trace a line back and trace a line there, that is a 90-degree rotation about the origin, okay? So that's where I'm ending up with that one. S double prime means, again, we're going to make the B value the opposite sign and make it first. So that's going to be 6, and then switch places with the A, so -2. So all I'm doing is following those little rules in the box up above. So 6, -2 is going to be 1, 2, 3, 4, 5, 6, -2, 1, 2. Boom, so that's S double prime. And there we go, so it would look like that. And again, if I were to draw a line back and draw a line segment over, again, that's a 90-degree rotation about the origin. So you can do a composition with reflections and rotations, and they are still rigid, meaning that everything, length and measurements are preserved. Okay, last box of the lesson, box number 6, is all about identifying rotational symmetries. So the definition for us that we're going to be working with, a figure in the plane has a rotational symmetry when the figure can be mapped onto itself by a rotation of 180 degrees or less about the center of the figure. So this point down here as an example has, the center point is called the center of symmetry. So this figure right here has rotational symmetry. So if I had the original figure at 0, if I rotate this figure 90 degrees, you'll notice that it ends up being the exact same figure as before. So it's mapped onto itself. That's what this part means, mapped onto itself. So if I rotate this 90 degrees, it gets mapped onto itself. Notice that 45 degrees is not necessarily a rotational symmetry. It's just when I move it 45 degrees, we're not able to map it back onto itself. So 45 degrees doesn't count, but notice that 90 does, and notice that 180 does. So these two images are the exact same as before. That's what it means to be mapped onto itself. So let's take a look at these ones down here as a quick example. I have 3 figures that we've got A, B, and C, the parallelogram, the octagon, the trapezoid. It says, do these figures have rotational symmetry? If so, describe any rotations that map the figure onto itself. So for part A, I said it has 180 degree rotational symmetry, and here's why. So if I kind of take this and I rotate this 180 degrees, so there's 180 degrees, and then can I map that back onto itself? Yes, I can. So 180 degrees is going to work for us, okay? In this one, I said 45 degrees, 90, 135, and 180. So here's how I came up with that, right? If I go 45 degrees, so 45 degrees kind of looks just like that one little turn. Can I map this back onto itself? And yes, I can. So 45 degrees counts. What about 90 degrees? There's a 90-degree rotation. And can I map it back onto itself? Yep, I can. So 90 degrees is going to count. 135 degrees, is going to look like this. So keep turning the thing. And does that map onto itself? And yes, it does. And then lastly, 180 degrees. If I rotate again, does that map onto itself? And yes, it does. So this particular shape, the regular octagon, has 4 rotational symmetries. Okay, and then the last one, part C, I said actually there were no rotational symmetries, right? So I drew the diagonals in all of them because that kind of helps you where that center of rotation would be. But in this case, right, I can't, if I start with this, I'm starting at 0, I'm good to go. But if I rotate this thing any degree, and there's 180, and it still doesn't map onto itself, the only way this maps onto itself is if I go a full 360. So because it doesn't fit the definition of a rotational symmetry of 180 degrees or less, this particular shape has no rotational symmetries. So there's a couple of examples of how you might see this stuff. Okay, that's box 6 and everything you need for this lesson.